In the last few lectures, we have been studying about push-down automata, and we have seen the working of push-down automata, and we have also seen in detail how push-down automata actually works with the help of examples. Now, in this lecture, we will be studying about the equivalence of context-free grammar and push-down automata. So if you remember, when we first started studying about push-down automata, I already taught you that push-down automatas are used to accept the languages generated by context-free grammars. So there is a theorem which says that a language is context-free if and only if some push-down automata recognizes it. So a language is said to be context-free only if some push-down automata can recognize it. So that is what we are going to prove, and hence we will find that the context-free grammars and push-down automatas are the same. The same means that the language generated by context-free grammars and the language accepted by push-down automatas are actually the same class of languages. So that is what we are trying to prove. So the proof is divided into two parts. We have part 1 and part 2. Part 1 says that given a CFG, show how to construct a PDA that recognizes it. That means if we are given a context-free grammar, we have to show how we can construct a push-down automata that recognizes the same kind of languages that is accepted by the given context-free grammar. And then part 2 says, given a PDA, show how to construct a CFG that recognizes the same language. So part 2 is just the reverse of part 1. So in part 1, we were given a CFG, but in part 2, we are given a push-down automata. And then we have to show how to construct a context-free grammar that recognizes the same kind of language that is accepted by the given push-down automata. So these are the two parts that we have in our proof. And in this lecture, we will be discussing about part 1, which says, given a CFG, show how to construct a PDA that recognizes it. So we are going from CFG to PDA, which we will be discussing in this lecture. Alright, so now let's see how we can do this. So for doing this, we are going to prove it using construction. That means we have an example given and we will show how we can construct a PDA for a given context-free grammar. So here we are given a grammar which says S gives BS and also A gives 0A and also epsilon, and B gives BB1 and also 2. So we don't have to worry too much about the productions that this grammar is giving, but what we have to do is, if we are given this grammar, we have to find or build a push-down automata for this grammar. So if we are able to build a push-down automata for this context-free grammar, then we are able to prove part 1. That is, if we are given a CFG, we are able to construct a PDA, and hence we will be able to prove the theorem which says a language is context-free if and only if some PDA recognizes it, and hence we can say that CFG and PDA are equivalent. Alright, so let's see how we can do this. So here what we are going to do is, we are going to take the leftmost derivation from this grammar. Now what do we mean by leftmost derivation? When we studied about a regular grammar, I already taught you what are leftmost derivation. So in leftmost derivation, what we do is, we expand or we consider the leftmost non-terminal that we have in our production, and we keep expanding the leftmost non-terminal until we reach the required string. Alright, so let us see. First of all, we start with S, which is our start symbol. This is the production we are considering, and we take S over here, and if we expand S, we see that S gives BS and also A. So let me take this production which says S gives BS. So S gives BS. So this is what I have. Now in this BS, if we see, there are two non-terminal symbols, B and S, and we have to see which is the leftmost non-terminal. The leftmost non-terminal is B, so we have to expand this B. Now this B, it has a production which says it gives BB1 and also 2. So let me take this one which says BB1. So instead of this B, I write BB1, and then this S, it comes down as it is. And now if you look at this one here, which is the leftmost non-terminal, it is B. So we have to expand B now because we are considering the leftmost derivation. Now if you look here, B, it gives 2 also. So I am going to take this production now which says B gives 2. So instead of this B, I write 2 over here, and now this is the production that we have, and here which is the leftmost non-terminal, it is B now, because 2 is a terminal symbol, following which we have B, which is the non-terminal symbol, and this is the leftmost non-terminal. So now I have to expand this B, and for that also I take the production which says B gives 2, so I write 2 over here instead of this B, and this 1s, it comes down as it is. Now if you look at this one here, 2, 2 and 1, these are all terminal symbols, and then the only non-terminal symbol that we have is S, which is also the leftmost non-terminal that we have. Now if I expand S, I have a production which says that S gives A. So instead of S, I write A over here, and in this one also A is the leftmost non-terminal, and if I expand this A, what do I get? There is a production which says A gives epsilon. So I will replace this A with epsilon now. So finally I just get 2, 2, 1. This is the string that we get. So this is how you expand the production using the leftmost derivation. And now one thing I want to tell you is that during this leftmost derivation, any of the forms that you are getting many productions over here, many forms are there. So any of the forms that you get during a leftmost derivation is known as a left sentential form. Now we will see how can we put this into our PDA, or how can we design a PDA for this kind of productions of the grammar that we have. Okay, so here I am writing this in a general form. So here we have different forms, as I told you, in left sentential form, and here let's say if I take this one, here I have 2, 2, 1. These are my terminal symbols, and this is a non-terminal symbol which is yet to be expanded. So I can write it like this. So I have A, which represents my terminals, and then this represents the rest of the symbols that have to be considered. So here I have B, which is a non-terminal, then I may again have a terminal, and again I may have a non-terminal B and another non-terminal C. So just for understanding, I am writing this in a general form where these are my terminals and these are the rest of the symbols which are yet to be considered. So if you have a push-down automata, these are my inputs, and this part, it represents the terminals which I already told you, and we assume that these terminals are already scanned, and then the rest of the symbols that are yet to be scanned, that is stored in the stack. So we know that in push-down automata we always have a stack, so the rest of the symbols will be stored in the stack of our push-down automata. Alright, now this general form that we have, let me put it into this push-down automata and show you how it actually works. So here I have my push-down automata, and then the terminal symbols which have already been considered in the input, A, these are the input symbols which is written here, and then I told you that the rest of the symbols which are yet to be scanned, they are stored in the stack. So I showed you there that BA, BC was there, which was yet to be considered, so I put them on the stack, and Z0 is the bottommost element of the stack. So when I taught you push-down automata, I already told you we always put an element at the bottommost of the stack. It is either represented by Z0 or sometimes by the dollar symbol, and this is used to represent the bottommost element of the stack in order to know when we have reached the end of the stack. So Z0 is there, and then the rest of the elements are stored on the stack like this, BA, BC, and then here I have just tilted the stack to the left in order to make you understand. Don't get confused, this stack and this stack is just exactly the same thing. I have just tilted it to the left in order to make it look sequential and continuous. Alright, so we assume that we have been expanding a production using the leftmost derivation, and during one of the left sentential forms we are getting this. So we are doing the leftmost derivation, and we assume that we have got this A which are already scanned, and this BC is what is remaining. So don't get confused, just think that you are expanding some production just like I showed you in the beginning, and then this is one of the stages that you encounter where these are the things that has already been expanded and these are the things that is yet to be done. And then what we have to do is at each step expand the leftmost derivation. So I already told you in leftmost derivation what we do is we always expand the leftmost non-terminal, but when we do it in our push-down automata, how do we actually do it? We have to do it using our inputs and stacks and all this. So how do we do it using the push on automata? So let us say that we have a rule which says B gives ASA X BA. So let's say this is one of the rules. So what we do is we check if the top of the stack matches to any of the rule. So this is my stack. Okay, it is just tilted down, don't be confused. So the topmost element of my stack is B. So I check that in my set of productions, do I have a rule in which B is there on the left hand side? That means, does B have any production? So we see that yes, B is having a production and it gives ASA X BA. So how do we proceed if we find it? If we find it, what we do is we have to pop this B out, and instead of this B, we will push the right hand side of the production that B was giving. So here we see that B gives ASA X BA. So this B will be popped, and instead of this B, we will push all this right hand side onto the stack. Alright, so this is how we do it. ASA X BA, B is popped and ASA X BA is pushed onto the stack, and then the rest of the things ABC, they remain as it is. So ABC was already there, and on top of that we push this production, the right hand side of the rule. Alright, and this was already the things that were already scanned, so they are here as it is. Okay, so this is the state that we reach when we do this. So what we do is we match the stack top to a rule. The stack top, which is this one, we match it to a rule. Is there any rule that is matching to the top of the stack? And if it is there, pop the stack. That means pop the topmost element of the stack which was matching the rule, and then push the right hand side of the rule onto the stack. And we just push the right hand side of the rule to the stack. So that is what you have to do when you have a non-terminal on the topmost of your stack. Alright, so let us now try to draw the transition diagram and represent it in form of a push-down automata. So as I told you, if you have a rule of the form A gives B, C, D, then you have to just add it to the push-down automata. And how do we add it? I told you, you have to match this A with the top of the stack, and if it is matching, then you have to pop that A from the top of the stack, and you have to push the right hand side onto the stack. So this is the PDA for that. So we have one state here and we have another state here. So this is epsilon because the input is not advanced. You don't have to advance the input. And then if you are seeing A here, you have to match it to the top of the stack. If it is matching the top of the stack and the rule, then you can pop it. You can pop it, and then you have to push BCD onto the stack. This is the right hand side of the rule, and that is pushed on to the stack. Alright, so this is how you do it if you have a rule of the form A gives BCD, and if this is the topmost element of the stack. Now one thing you must have noticed is that we are pushing three elements B, C, D onto the stack. But you must be knowing that we cannot just directly push three elements all at once to the stack. You cannot push more than one element to the stack at one time. You can only push one element to the stack at one time. So if you want to push BCD to the stack, you will have to make more transitions or more states in order to achieve this, like this. So if you want to push BCD, you need to use more states like this in order to do it. So we see that here this epsilon is this epsilon over here, and then we are matching this A to the top of the stack, and the rule that A is matched over here, and then we are first pushing D onto the stack. We are pushing D, and after pushing D, this epsilon remains epsilon because this is epsilon over here, and then now we don't want to pop anything, but we are pushing C, and then here also we are not popping anything, but we are pushing B to the stack. Now we are creating these states just in order to accommodate this B, C, D. And then if you see that we have been pushing this in the reverse order, we have been doing D, C, B instead of B, C, D. And why is that? That is because that is the right order in which you should be pushing elements to the stack. So let us see if this is your stack that you have over here. You first push D, and then you push C, then you push C, and then you push B, So when you look, it comes in the order B, C, D, but you have to push it in this way. First D, then C, and then B. So that is why we are pushing it this way. Okay, so now we have understood what we have to do if we have rules of this form, and we have seen what to do when we encountered this kind of rules when we have a non-terminal on the top of the stack. Now let us see another condition. Now let us say that we have a rule of this form. A gives 0, 1, 0, 2, B, 3 and C. So we know that what is our fundamental rule? Our fundamental rule is that whenever we see a non-terminal, we have to match it to the top of the stack, and if it is matching, we have to push the right hand side to the top of the stack. So let us assume that we already encountered this A and then we matched it to the rule. Let us assume that this A was on the top of the stack and then we matched this A to one of the rule that we had, and this is the rule that we had. So what we did, we have already popped A and we have pushed this on top of the stack on top of whatever was there. So this is the stack that we have. So let us say that something was already there in the stack, Z0 being the bottommost element, and let's say that we encountered A. A was the topmost element on the stack at this point, and then we match that A with one of the rules, and then when we match, what will we do? We pop that A and then we push the right hand side. So this is the right hand side, 0, 1, 0, 2, B, 3, C. So 0, 1, 0, 2, B, 3, C is pushed on top of the stack after popping A. Now if you look at this stack, you see that the topmost element of this stack is a terminal symbol, which is 0. Now in the last rule, I have told you if you encounter a non-terminal symbol, what you have to do, and we know what to do. But if we encounter a terminal symbol, then what do we have to do? So if you encounter a terminal symbol, what you have to see is you have to look at the input. This is our input, and you have to see if the next input that is going to be scanned and the topmost element of the stack are matching or not. So we see that the next input to be scanned is 0 and then the top of the stack is also 0. So they are matching. So what you have to do? You have to pop this 0 from the stack and then you have to advance the input. It comes to the next one. So remember that in the previous rule, we were not advancing the input. But in this one, when you have a terminal on top of the stack, you match it with the input and then you pop it and then you advance the input. So now it comes here and again it checks. Here we have 1 and then here also the next one is 1 because 0 is already popped, and since they are matching, this one also will be popped. Then it checks 0, 2 in the similar way. 0 and 2 will be checked in the similar way and they will be popped, and the input advances till here, and then after that we get B, which is a non-terminal symbol. And then if you get a B, what do you have to do? You have to apply the rule that we studied just before this, and then it goes on like that till we reach the end of the stack. So what you have to do is match the terminal symbols to the stack top and pop them. So if you have a terminal symbol, this is what you have to do, and this is the push-down automata that I have designed for this. So it actually means that when you have a terminal symbol, you have to see if the terminal symbol is there and you have to pop it from the stack and don't push anything onto the stack. Just advance it but don't push anything. So even if you have 1 or Z, whichever terminal symbols are there, you have to just match them, pop them and don't push anything. So these are just some terminal symbols. For example, I have written, and then this is the general form X. If you have X, so X is popped and nothing is pushed. And what is X? For all X belongs to sigma. Sigma denotes the set of terminal symbols. This is one of the basic notation that we have studied from the start of this lecture series. Sigma denotes the set of terminal symbols. Whenever you have a terminal symbol, then you have to just advance the input, pop it and don't push anything onto the stack. So this is what you have to do whenever you have a terminal symbol. So now we have already studied that whenever you are doing this, if you encounter a non-terminal symbol, we have learned what to do, and if you encounter a terminal symbol, also you have learned what to do. Now let us design the final PDA for this, and let us see if we can actually design it or not, so that we can prove our theorem. So here we have the final push-down automata for our context-free grammars. So here we have our starting state, and in the starting state, what do? We don't read anything, we don't pop anything, but we push Z0 onto our stack. And why do we do this? This is the basic and first thing that we always do in every push-down automata. We used to push an element on the bottommost of the stack in order to denote the bottommost element of the stack, so that we can know when we have reached the end of the stack. So Z0 is first pushed onto the stack, and then what do? We see that we are pushing the start symbol onto our stack, because every production we start with the starting symbol, which is denoted by S. So we first push the starting symbol, and then we come to this transition where we have many rules over here. And then what are they? These are the rules that we just studied before. So if we have a terminal, then what do we have to do? We have to advance the input, and we have to pop the terminal symbol, and we don't have to push anything onto the stack. So this is for all the terminal symbols. And then what about rules? If we are getting rules, that means non-terminals, then we don't advance the input, but we match the top of the stack with the rule, and then we pop that element, that is the left hand side or the topmost element of the stack, which should be the same, and then we push the right hand side of the production to the stack. So this state over here, it is just a generalized way to denote all the transitions that we have if we get a terminal symbol or a non-terminal symbol. So when you practically design it, this will not be one state, this will be many states. You have to design multiple states in order to do all this, but in order to make it simple and to accommodate all this, I have just drawn one state here showing all the different transitions. So after doing all this, we come to the final state when we encounter Z0 at the end of the stack. So after doing all this, if we find that our stack is empty, that is Z0 was the first element that was pushed to the stack, and if we at the end, if we find that Z0, then we can pop it, and then we make sure that we have reached the end of the stack and we don't push anything, and at that time you can come to the final state, and hence that language generated by that context-free grammar will be accepted. So this is how you design the pushdown automata for the context-free grammar, and we see that in a generalized way we were able to design the pushdown automata for the context-free grammar. So hence we were able to prove our theorem, which said that a language is context-free if and only if some pushdown automata recognizes it. So part 1 we were able to do it. We were given a CFG and we could construct the pushdown automata that was able to recognize that CFG. So this is how you prove the first part, and from the first part we can say that context-free grammars and PDA, they are equivalent. So I hope this was clear to you. In the next lecture we will be seeing the second part of this proof. So thank you for watching this, and see you in the next one.